test. All right, good morning. Let's get started. I do have one page handout, so I wanted to give it to you. All right, so let's continue on this solution to second order homogeneous linear ODE with constant coefficients. So the format of this type of ordinary differential equation is like this: y double prime plus ay prime plus by equal to 0. Right. Now, of course, you can also have a format of this like this. So like a ay double prime plus by prime plus cy equal to 0. And this is probably more general. So, but bear in mind these two, okay, these two here, there's literally no difference. If you normalize the second one, dividing a by both sides, then you get exactly the format like what's given over here, right? So there's no difference at all. In the handout, I actually use this one to illustrate the formulas that you can make use of. So the question is, we want to obtain a solution of this. In the previous lecture, we have shown that, okay, the key is to create this characteristic equation, the quadratic equation based on the second order differential equation. The coefficient of quadratic function is exactly the same as coefficient of the second order differential equation. Okay. Then we're going to be able to obtain a solution based on the solution of the quadratic function here, or quadratic equation here. Okay. Yeah. So the solution for this quadratic is lambda 1 and 2 equal to negative a plus minus a squared minus 4a divided by 2. So this is a solution for this one here. If your quadratic equation is written in the format of a lambda squared plus b lambda plus c, then you have a slightly different appearance. Okay. So now we have, okay, we can obtain three different cases. Okay, 3 different cases based on this square root term. So the first case is when you have 2 distinct real roots. And that's when this a squared minus 4b is greater than 0. So the square root term is more than 0. So you get 2 distinct real roots. And what are the 2 real roots? So whatever the coefficient you plug it in, and you get one is lambda 1 and lambda 2. Right? So basically you get these 2 real roots. So based on the 2 real roots, then you have basically you're going to have two particular solutions. One is y1 of t equal to e to the power lambda 1t. And the other one is y2 of t equal to e to the power lambda 2t. So the two solutions for the lambda will enable you to obtain two particular solutions for the second order differential equation, which is this one here. Okay. And one is the e to the power lambda 1t, the other is e to the power lambda 2t. Okay. And you can also easily show these two functions. These two functions, they're linear independent of each other. So this e to the power lambda 1t and e to the power lambda 2t, they are Li. So they're not depending each other. If they're not depending each other, remember the three theorems that we introduced from the previous lecture. So you got two particular solutions and they're linearly independent of each other. Then the general solution, right? The general solution is basically y equal to c1, y1 plus c2, y2. C1, C2 are two constants that can be determined by initial conditions. So then you plug in y1, y2 at here, you get c1 e to the power lambda 1t plus c2 e to the power lambda 2t. So that's the most, actually, the easiest case among the three different cases. Okay, so you got two real roots, and your general solution is basically based on the two real roots, lambda 1 and lambda 2. All right, so let me show you one example here. So let's say this is a second order differential equation with constant coefficients, and it's also linear, of course. And we'll be given some initial conditions. So the initial condition says y at the time equal to 0 is 4, and y's derivative at a time equal to 0 is 5. Let's solve this differential equation. And the steps is very straightforward. You based on this, you create your characteristic equation. So here's your characteristic equation based on the second order differential equation. Now we typically would use a lambda, and it's a variable here for the characteristics used, typically lambda. Of course, it's strictly speaking, you could use any other variables. It's just sort of convention. Then from here, you try to solve for the lambda. Okay? So you can either use the formula, just use this formula to solve for the lambda, right? But just be careful that the formula I wrote down at here, okay, only works when the coefficient for lambda is 1. But the one I gave it to you, so the one I gave it to you is more of a general case. So the one I gave it to you, you have a quadratic function assuming not a 1 coefficient in front of lambda x lambda square. And so this is a more general formula for that one. So just as long as you know the general formula is fine. Now, if you have practiced, if you know this well enough, you could also write this quadratic function into two factors. Yes. Oh, sorry, yeah, minus 1, minus 2. Yeah, good point. Okay. Yeah, often in time when I give you a question, you probably will be in this kind of case. You could just factor this quadratic function into two factors. So then this will be easier. So you get lambda equal to -2, lambda equal to 1. So then you can form your general solution, right? Is C1 e to the power lambda 1. Lambda 1 is -2t. And then C2 is e to the power lambda 2, which is t. So that gives you the general solution for this second order differential equation. So now let's find the C1, C2 value based on the initial conditions. So how do I use it? We have y of 0 at t equal to 0 equal to 4. So this equal to 4. So when t equal to 0, you plug t equal to 0 here and here. E to the power 0 is 1. So it's C1 plus C2. That's y of 0. So now you have one equation, right? C1 plus C2 equal to 4. And then next, first calculate the derivative of the general solution. So you get -2 C1 e to the power -2t plus C2 e to the power of t. So now I applied my initial condition. The derivative value at t equal to 0 is equal to 5, -5. Sorry, actually -5. Okay. Then you plug t equal to 0 into the derivative term here. You go to -2 C1 plus C2 equal to -5. So two equations, two unknowns, solve them, and you get C1 equal to 3, C2 equal to 1. So then you can plug it back into this function, and here you get y of t equal to 3 e to the power -2t, and then e to the power t. Because that's the solution based on the initial conditions. Right, so this is very straightforward. Huh? Yeah, given this case number 1, when you have two real distinct roots. Any questions on this case? Okay, good. Now let's take a look at second case. Okay, and that second case basically is when the square root term, okay, it's gone. It's 0, meaning whatever under the square root give you a 0 there. So in that case, we got two repeated, I should say one repeated roots, lambda. So you don't have one solution, right? But it's repeating twice, basically. Okay. So if I go back to this here, if this is my characteristic equation, if a squared minus 4b equal to 0, then your only solution is -a over 2. So let's write it down here. A squared equal to 4b. Lambda equal to -a over 2. So you could write it just basic, it's repeating twice, so there's only one lambda basically. Okay, if there's only one lambda, then I can certainly create a particular solution. So that give me one particular solution at here. Okay. But I need two particular solutions, right? If you want to find the general solution, you need two particular solutions, like the case 1 here. So you need another one, and also you need the other one to be linear independent of it. Then you can create your general solution. Okay. Yeah. So the question here is only have one. Then what will be this y2 of t? How do I find another particular solution? So here's a way of a train of a thought set here, how you find the other particular solution. There are different ways of doing it, but then this is more of it. So you let this y2 of t, okay? So you would think, basically, people think is maybe y2 of t, okay, it will look like y1 of t, but it won't, of course, it won't be, it will be different. And also you want it to be linear independent of this. So let's say, for example, right, if y2 of t takes the format of y1 of t, you can't just let it equal to e to lambda, because then they're literally dependent on each other, right? So then what do we do is we say, okay, let's multiply this e to the power lambda t, which is the solution, right? The one particular solution, with another time function, call it v of t, in hoping that this y2 of t, okay, could be found if we can find a v of t. If we can find v of t, and the y2 of t is also a solution of this second order differential equation, then obviously, right, as long as this is not 1, then y2 of t will be independent from this y1 of t. So that's the idea. You create a y2 of t in this kind of format. So basically, it's v of t times y1 of t. So if I have to write everything out, so v of t e to the power negative a over t in this case. Okay, then we need to find v of t. See if this v of t exists or not. And such that y2 of t is a particular solution. Okay, so that's the train of thought. So how do I find this v of t so that y2 of t is a particular solution then? So what we can do is, there's a little bit of details here, so I'm going to skip a little bit detail. So this is the how you do here, the steps. So calculate y2 of t prime. This is your y2 of t. And also calculate y2 of t double prime. Right? So keep this v of t as unknown. When you calculate the derivative, you're going to use the product rules. So there's going to be a little bit writing here, so that's why I'm skipping the details. You calculate these two, and then substitute into this y prime plus ay prime plus by equal to 0. So basically substitute back into this second order differential equation. If you do these two steps at here, there's a little bit of writing, and carefully do it, and you'll be able to find that you'll be able to find this v double prime t equal to 0. So if you do this step, find it here, then the only solution to make it as a solution is this particular solution is v double prime of t equal to 0. So what does v double prime of t equal to 0? When a function's second order derivative 0, that means its first order derivative must be yes, right? Must be constant. And then that also means the function itself must be something like this, right? So at plus b. Okay. Now, you're not looking for a general solution v of, you're only looking for, as long as I can find one solution for the v of t, then I'm happy. And I don't need a very complicated one. So in this case, I'm going to choose v of t just to be t. So that means my y2 of t is t times e to the power negative a over 2t, okay? Or e to the power that's lambda t. Okay, lambda is the one repeated root. Okay. So now you can see this is a particular solution, and this is also a solution that's linear independent of the y1 of t. All right, so y2 of t is Li from y1 of t. Then I can apply the theorem number 3. My general solution is y equal to c1 y1 of t plus c2 y2 of t. So you write it out. Basically, c1 e to the power lambda t plus c2 t times e to the power of lambda t. So that gives you this general solution for the second case. When you have one repeated roots, right? So what is the general solution? So if you look at your handout, you will see, and that's basically what we have over here. Okay. Okay, so let's take a look at quickly look at example. Okay, let's say we have a second order differential equation taking a format like this. First step, you write down the characteristic equation. Okay, based on the coefficient of the function, the equation. And then you can apply the formula to calculate the lambda. Okay. Or you can, if you observe, and you probably will be able to observe that this is right, this is the same as lambda plus 0.5 bracket to the power 2. And you can verify easily lambda squared plus 2 times 0.5 times lambda, then plus 0.5 squared, and that's what you get, right? So obviously, your lambda's solution is just 1, is negative 0.5. So that's the case number 2 we're handling here. So in the future, you don't have to go through all the derivations. You can just make use of the results. As long as you know it's case 2, you can apply the results right here. So your general solution is C1 e to the power negative 0.5t plus C2t e to the power negative 0.5t. And that's it. So that's the general solution for this question. It's quite straightforward. Okay. So I don't think there's more complicated situations than this. There's no trick here at all. All right. So that's case number 2, right? So case number 3 is probably the most complicated case among the 3, but okay, so that's when you have 2 complex conjugate roots. So complex conjugate roots, you go back to the all the way to the top here. Basically, whatever underneath the square root, okay, give you a negative number. Then you got a complex conjugated roots together, okay, for the whole solution for the lambda. So that's when a squared minus 4b is less than 0. Okay, or in general, you just have to remember the terms underneath the square root is less than 0. All right, so then in general, if I use my notations written at the top, the 2 complex conjugate number, right, can be written as, so remember this is square root a squared minus 4b, right? This is this square root here. And because this is a negative number, so you can write it as a j and 4b minus a squared. And then this solution here is just negative a plus minus j 4b minus a squared and divided by 2. Or you could just write it as a general format. Because it's a complex conjugate, so I'll just write it as a real part plus minus the imaginary part. And that applies to all different situations, right? So that's also applied to the situations here when your general quadratic function in this format, and you also have basically complex conjugate. So whatever the real part and imaginary part, and that's based on your calculation of your, based on your characteristic equation. Okay. All right, so bear in mind, essentially what you get here, okay, you get lambda 1 equal to alpha plus j beta, lambda 2 equal to alpha minus j beta. So you still got two solutions for lambda, and they're different, except they're complex numbers. So technically, right, what I could do, right, as remember case number 1, when you get two real distinct roots, how we create the general solution, right? We create a general solution, basically y equal to c1 e to the power lambda 1t and c2 e to the power lambda 2t. Okay. So technically, you could see, okay, then the general solution is y equal to c1 e to the power lambda 1t, c2 e to the power lambda 2t. Okay, so you're using exactly the same approach, and that means it's c1 e to the power lambda 1 is alpha plus j beta times t, c2 alpha minus j beta times t. You create a general solution exactly in that fashion. But you certainly will see a problem here, right? I mean, what I write it down, it is actually correct, but the problem is this is a complex number. So e to the power of a complex, you still get a complex number, okay? But the y here, okay, is supposed to be the solution to the second order differential equation. So y will not be complex number. Okay, so y has to be a real function. So if this is a complex number, this is as a matter of fact, complex function. This is a complex function here, but this is a real function. So the C1 and C2 here, they must have to be also complex, right? So the only chance that you can give you back a real is when you have a complex times complex. Okay. So the C1, C2 here, okay, has to be two constant complex numbers. And that's the idea. So C1 and C2, and they have to be, they still have to be constant, but they are complex numbers now. And only that will make this solution work. But I don't think you will be keen trying to find what C1, C2 are, okay, based on certain initial condition, because that makes the computation probably too complicated. Okay. So we want to find a general solution, not exactly in this format. Okay. So then what should we do, right? Okay. So first of all, what we did here, right? You can see this is, let's see, this is y1, this is y, let's call this is y1a, and this is y2a. So let's call this y1a equal to e to the power lambda 1t. y2a equal to e to the power lambda 2t. And these two, if I write it out, this is e lambda 1 is this term at here. Okay. E to the power alpha plus j beta t. This is e to the power alpha plus minus j beta t. Now I'm going to use the Euler's formula. For this first term, alpha is a real term, so e to the power of alpha t, and e to the power of j beta t is cosine beta t plus j sine beta t. And this one here is e to the power of alpha t, then cosine beta t minus j sine beta t. Right. Those are the two particular solutions, right? Two particular solutions which are complex, but I don't want to use them. Okay? I want to find a particular solution that's actually real, a real function. So how can I create a particular solution that is real based on the two given particular complex particular solutions? So if you recall that in one of the theorem, that for the solution here, the first theorem, okay, look at the first theorem. It says if y of t is a solution, y2 of t is not a solution, then c1y1t plus c2y2t is also a solution. Right? So you can create a different solution using this theorem number 1. Right? So then let's create a different solution at it here. Right? Yeah. So I'm going to create the first solution. I'm going to create 1/2 y1a plus y2a. So I'm going to create one solution using this expression. So essentially, I'm adding the two particular solutions up and then divided by 2. It's like a C1 equal to 1/2, C2 equal to 1/2. So then what does it give us? So you can clearly see, because you got a negative imaginary, positive imaginary. So when you add these two up, the imaginary part is actually disappeared, right? So you end up with just e to the power of alpha t and then cosine beta t. And that's a real function. And according to the theorem number 1, this is also a particular solution. Okay. So that's good. So I've achieved half of the, so this y of y2 of t here. And the next one, we create, how to create another particular solution is we use the first one minus the second one, okay, and then divided by 2j. Divided by 2j. So you might argue, how could you divide by, yes. So here, it never saying this is a real constant, it just says a constant, right? So you can certainly do that. And you can see if you use this one minus this one here, the real part actually will delete it from each other, and you have the imaginary part becoming adding together with the g. So that g will cancel this g here. So you end up with e to the power of alpha t sine beta t. So now we successfully created two particular solution, two new particular solution, which are real. And they are also linear independent of each other. Okay. So that y1 of t, you can easily show that y1 of t, y2 of t, they are linear independent of each other. So if you're linear independent and there are two particular solutions, then guess what? Then the general solution is y of t equal to C1 Y1 plus C2 Y2. And that give us, so this time instead of using C1, because I already have C1, C2 here, when we create this using the complex conjugate. So let's use a different symbols constant here. Let's call this is A and this is B here. Okay. Just as long as it's constant, it's fine. So y of t equal to A e to the power of a t cosine beta t. B this is the general solution when the roots are complex and conjugate. Right, so this is the same in your formula sheet. It's in the table, okay, which is over here. Okay. So that's the case number 3, right? What's the key for case number 3? The key in case number 3, I mean, you certainly, you're going to use this final result is to get what is the real part, alpha, what is the imaginary parts, beta, right, based on the solution of the characteristic equation. So let me show you an example. So let's look at this weird quadratic function. This one you might not be able to factor. You have to use your calculator probably, or use your write down the roots first. So first create the quadratic function, the characteristic equation. So in terms of formula, what do you want to use? I mean, you can certainly use this formula here. Right? This formula basically, in this case, A equal to 1, B equal to 0.4, and C equal to 9.04, right? And you plug it into this formula, and you calculate lambda 1 and lambda 2. So you get your lambda 1 and then 2 equal to negative 0.2 plus minus j 3 over root 10. So sometimes you don't need to calculate what root 10 is. Just keep it as a whatever this clean expression, 3 over root 10. That's fine. Okay. Or you write it as a 3 root 10 divided by 10, and that's fine too. Okay. So obviously this is a complex conjugate, a pair of roots. So write it as alpha plus minus j beta. So alpha equal to negative 0.2, beta equal to 3 over root 2. All right, so once we get this step, okay, now since we already derived the results, so all you need to do is to apply the results at here. So that's pretty straightforward. So your general solution for the question is A times e to the power of alpha t, which is negative 0.2, and then cosine beta t, which is 3 over root 10. So that's the first part. And b e to the power negative 0.2 t again, sine t here, right? 3 over root 2 t. Hang on a second here. I think I don't know why I have a root 10. As a matter of fact, all right, the answer here is just a 3. Oh, I have a root 10 there. Sorry about that. It's just a 3 here. Okay. Yeah. So that's your general solution for this one. You've got two complex conjugate roots. You apply the formula and you get general solution here. So let me show you another example. So here's another example here. So the y prime plus omega square and y are equal to 0. So for this example, there's a term missing. So there's no y prime term, but that's okay. If there's no y prime term, basically means the coefficient for the y prime is 0. Right? So the b is 0 there. So you can still follow exactly the same approach. Okay. Create the characteristic equation, lambda square plus omega square equal to 0. The solution for lambda is positive and negative omega. And it's, sorry, G, yeah. It's complex conjugate roots. There's no real part. So real equal to 0 and beta equal to omega. Okay, so then you get y equal to basically a times cosine omega t plus b times sine omega t. You got a solution like this. And I'll show you a little bit one example here, how you can actually, what kind of application, physical application will give you this type of equation, okay? And what exactly does this actually do here, okay? Now, I want to extend from this example just a little bit at it here, and from this example. As you can see from this example here, the result is a cosine omega t plus b sine omega t. So the cosine and sine here, so technically, this is like cosine theta plus b sine theta, right? So the sine and the cosine have the same angle, except a different amplitude possible. Okay. Now, you can always, when you have an expression like this, you can always actually put it into a single expression, okay, and a single expression here. So I want to show you, I'm not going to show you the detail how you do that. Essentially, in general, you can take a look at the lecture notes, how it's done. When you have an expression like this, a cosine and a sine adding together, okay, same angle, like cosine omega t at here. Okay, you can combine it into one single sinusoidal function, and that is square root a squared plus b squared, and then cosine theta minus phi. Cosine theta minus phi. And the phi out of here is tan inverse b over a. The phi is between negative pi to pi. So this is a general formula. But when you use this formula, there's a little bit of, sometimes a little bit of detail you had to be just to be a little careful in terms of how you get this phi value. Okay? And that really depending on the location of A and B. But you can see here, right? In your mind, you should keep in your mind is, because when I add a cosine and sine term, that's the same angle, okay, or omega t, and it could turn into a different sinusoidal function. Okay, but now you got a phase angle showing up at here. Okay. This phi, which is given by the inverse tan. You can look at lecture notes. I actually have two different ways to prove this. To this expression in here. So let me give you one example. let's say I have -3 cosine omega naught t plus 4 sine omega naught t. So let's say I'm adding these two terms together, and I want you to express this expression in a single sinusoidal function. Right? So what do I do? Basically, I want you to write it down like this. So you will write down first a equal to -3 and b is 4. And then what you're going to do is, right, you could do something like this. Okay, label the location of a and b. So a is -3 here, and b is 4 at here. So given the -4 and -3 and 4, this is how you're gonna define the phi angle. Okay, the phi angle here. So now you can calculate, okay, using your formula. So that gives you -4/3. So this is where I want you to be careful. Can you use your calculator to, if I don't tell you anything, just use your calculator to calculate the tan inverse -4/3. What would your calculator give it to you? If you just calculate this one here. Excellent. So you get a -3.53. Okay. That's a 53 degree, right? Yeah. So your calculator will actually give you -53 degree, which is wrong. The reason is because, as you can clearly see, my phi angle should be a something 100 something, right? Yeah. So the calculator, because calculator doesn't know where the locations of the vector is. The calculator basically give you the angle from here to here. Okay. So you cannot trust your calculator completely. So in this kind of question, you have to label it, and then especially label it like this, what I have here. A is a term associated with cosine. B is a term associated with sine. Okay. And then you can find the phi angle properly. So that should be 126.9 degree. Then you can use the formula over here to get your overall expression. So let's say this is x of t here, and your x of t is equal to square root a squared plus b squared cosine omega naught t minus phi. Okay. Square root here is easy to calculate, which is 5. So cosine omega naught t minus 126.9 degree. And that's the pitfall that I wanted to point it out. I just, in case, you trust your calculator too much, and then you end up with the wrong answer, right? Okay, so before I still have 1 minute, so I can quickly just give you an example, okay, how actually you can have this kind of a second order differential equation. Okay. So if you remember a mass spring damper system. Okay. So let's say, for example, you have a mass spring damper system. There's no damper. There's only one spring. Okay. And there's also no external force applied to the system. So if you draw a free body diagram using Newton's second law, you can derive the second order differential equation, okay, for this system, which is mx double dot plus kx equal to 0. Right? And that's equivalent to x double dot k over m and x equal to 0 here, if divided by m. Right? So you can clearly see, right? This is the format of the y double prime plus omega square and y equal to 0. So the omega here is square root k over m. So the system, this mass spring system, will oscillate, right? As long as you have an initial condition, will continue to oscillate, okay, based on this given general solution at here, which is the cosinusoidal function. Okay. How does it oscillate? What's the amplitude of oscillation? That's based on initial condition. Okay, yeah. And this is actually called undamped system. Okay, so there's no damping, it is just continue to oscillate. Okay. All right, so I'm going to stop here, okay, and we'll look at more second order differential equation in the next lecture.